Hello, good day to everyone. I'm happy here today to present the topic iterative method for split equilibrium problem and minimization problem via conjugate gradient method at the International CMMSE conference and the second conference on high performance computing. My name is Jamilu Abubakar, and this is a joint work with Professor Kumam and Parin Chapunya from Kim Mangkut University of Technology, Chonburi, Thailand. So today, this is the overview of my talk. I will give some introduction, then preliminaries, main result, and numerical illustrations. So I want to recall the definition of a split equilibrium problem. Suppose we have H1 and H2 to be two real Hilbert spaces with closed and convex subspace C and Q respectively. And also F1 here and F2 to be by functions. Then the split equilibrium problem introduced by Modapi and further studied by Kazimi and Rexby is a problem of seeking a point in C such that this inequality is satisfied for all V in C. And at the same time, the image of that point in Q also satisfy this second inequality where A is a bounded linear operator from H1 to H2. And also for the minimization problem, we are considering here the problem of minimizing a function h subject to a point in C, which can be given by this. So these two problems can serve as a unified framework for studying several important problems with applications in engineering, image processing, game theory, economics, and many more. And over the years, a lot of iterative methods have been proposed and studied for studying and approximating the common solution of these problems. For example, see the references here, which I will show them at the end of the talk. And most of these iterative methods were designed based on fixed point methods such as man iteration, Halpern iteration, viscosity iteration, and so on. So having said that, it is well established as a fixed point method that a point U in C solve the minimization problem 3 if and only if U is a fixed point of some operator uh, PC given by this, where PC here is a metric projection onto a closed and convex set C. I is an identity mapping. Delta here is a positive number given some for satisfying some conditions, and here is the gradient of H. So consequently, this prominent iterative method, the gradient method, is being developed based on this fact that, and it has been shown that if certain conditions are satisfied, then this iteration now converges to the minimum value of the function. And some of these conditions that needs to be satisfied is the gradient here needs to be inverse or strongly monotone. And so in a situation where this operator now is not inversely strongly monotone or strongly monotone, then the whole of the operator here will fail to be contractive. And based on the contractive Maddox principle, then it's no more we cannot get the distance of the fixed point here. But there are other several approaches to approximating the solution of this problem. For instance, Zhu in this paper presented an operator-based method using averaging mapping, alternative to the iteration 4 here above. And another important aspect I want to recall here is the concept of conjugate gradient method, which we know is a method based on the acceleration of steeped descent method, where the direction of the steeped descent method is modified by given by this, where d naught is given by this. So recently, Chi and Lee used the idea of conjugate gradient method and from the fixed point formulation to propose a method for approximating the common fixed point of inclusion with regard to some maximally monotone operators F1 and F2, and solution or common solution of minimizing a function given by this method. where the delta here is in this, and the sequence is here, and this is a sequence of contractive mapping, and these are the resultant with respect to the maximally monotone operators f1 and f2. So in the method here, the conjugate direction here, which was defined based on the negative gradient of that function, was modified and replaced this gradient with an averaging approach. So this is a really interesting method in the sense that they don't need to depend on the strong assumption on this gradient to be strongly or inverse monotone for the existence of the solution using averaging approach. So we want to use the same idea here, but in our own case, we want to solve the problem, common solution of split equilibrium problem and and a minimization of a given function, which is a direct extension of somehow extension of the problem here defined by Chi and Lee. So in the second section here, I want to talk on the assumption that we considered on the underlying by functions here. F1 is assumed to satisfy these assumptions here. One is greater than or this inequality holds. The second one, that F1 is monotone, and also we assume it to be upper hemicontinuous, and we assume that for any fixed point, point here u1 in C, the function here is convex and lower semi-continuous. And also we require this lemma here, and we use this lemma. For the sake of time, I will just show the lemma. These are important for the convergence analysis of our method. So, and we use this lemma also to show the strong convergence. And now, before I give the main proposed method, I recall the definition of average mapping. Mapping Rn from this is said to be average if it can be written like this, where I is an identity mapping and An is in 0 and 1. So for the main result here, now we have this setting. We suppose have to have this by functions, two by functions. You can see satisfying assumption 9, and let F be a contraction mapping with a contraction parameter kappa given by this, and a bounded linear operator from H1 to H2 given by this, and adjoint denoted by this, such that we have these sequences in 0 and 1, and in here satisfying the following conditions from C1 to C5. And also we further assume that the function we are trying to minimize here is a real value convex function, and the gradient of that function is L Lipschitzian mapping with L as a positive number. And this has been shown that if we have the sequence in 0 between 0 and 2 over L, then this mapping here is 2 plus lambda NL over 4 average. And this fact can be found in this paper. And now, so we can see that this mapping can be written as an average mapping. And also throughout the, and here we suppose that the common solution set here is non-empty and is given by this, which is the intersection of solution of the split equilibrium problem and the solution of the minimization problem here, U. So for the algorithm here, these are for the initialization, we choose these sequences in this satisfying these conditions, and also we choose another this sequence also such that this C3 condition is satisfied. Now we choose a point in H1 and we define D naught by this. And for the iterative steps here, for any UN now, we can define Vn by this and delta n to be given by this. So if Vn is equals to Un, then we stop. We are at the solution of the split equilibrium problem. Otherwise, we compute Yn by this, and we update Dn plus 1 by this. And we compute in step 3 Un plus 1 to be this. So we set n is equals to n plus 1, and we repeat the system again. So for our first result here, this lemma is essential in showing the convergence of the sequence generated by the proposed method. So suppose we have UN be a sequence generated by the proposed algorithm, and we suppose that eta n satisfy this condition, then we have this relation. And for the main theorem here, we suppose let H1 and H2 be two real hyperspaces with C and Q being non-empty closed and convex subset of those spaces. And we have bifunctions F1 and F2, and we assume that this bifunction satisfy the assumption 9, and F2 is further upper semi-continuous in the first argument. And also we suppose we have a contraction mapping F with a constant K and a bounded linear operator A from H1 to H2 with an adjoint denoted by this. And we suppose that this sequence is there are sequences Varo here n in 0 and 1 and beta n satisfying the condition C1 and C2. Then given any point in C arbitrarily, then the sequence is generated by this proposed algorithm converges strongly to S in the solution set, where this S is given by the projection of this contraction at S onto the solution set. And also this can be seen as a unique solution of the variational inequality here for all U in the solution set. For the numerical illustrations, we perform all computation on MATLAB 2019B with computer specification by this. And this is the first example. Here we set H1 and H2 to be R, and we use the usual induced norm and inner product given by this. And we define the bifunctions F1 and F2 to be this. And so we can obtain T1 and T2 to be given by this. TF1 to be given by this, and for the control parameters we set the control parameters to be given by this, and for the contraction also to be given by this. So we can see this is the behavior of the algorithm here against this is a plot of error against the number of iterations. Then also for the same example, we try to show the behavior of this algorithm when we have different initial point and also different sequences. We can see with all the different initial point, with the algorithm is still stable, and also we see choosing the sequences here B in this second column tends to have faster convergence in terms of number of iteration and computational time. And for this second example here now, for this second example, for the second example here, we give an example. For this example, we give a comparative analysis. We compare our method with a method proposed by Kazimi and Rizvi in this C. So, and we take H1 to H2 here to add H2 to be in R3, and we define the closed and convex subspaces C and Q to be by this. So we can see that here the two compared, we donated the proposed method here to be algorithm 1 and the compared one to be algorithm 3.1. Clearly here we can see this one has converges faster than the compared algorithm, and it has less number of errors in terms of the tolerance here. So thank you for your attention, and this is some of the references that we use.